Hello, everyone. My name is Chen. Welcome to the class. I'm from Department of Mathematics and Statistics in Northern Arizona University. The lecture today is about the matrix algebra in landmark carbon cycle modeling, and it's going to cover some basic knowledge of matrix algebra, such as matrix operation like matrix multiplication, inverse matrix, identity matrix, inverse matrix, eigenvalue, eigenvectors, linear system. If you still have fresh memories on these materials, you may skip this lecture and go ahead, take a look at the quiz problems and have an assessment of this material yourself. And if not, I would suggest you go through the lecture today with me. So let's start. The ultimate goal in this lecture is to answer the question raised in problem 1, which is a simplified carbon transfer model. Suppose that you now have this simple model that 3% of the carbon in the fast soil pool moves to the slow soil pool each year, and also 95% of fast soil pool stay the same, while in the slow soil pool, 1% move to the fast soil pool, and then 97% of the soil pool stay the same. We don't consider, yes, you may notice that there are 2% lost in both pools, or we don't check those, and we assume that no further influences on these two pools. So our question is, what are the pool sizes after 10 years, 50 years, 100 years? So this is a very simplified model because we're assuming a fixed constant rate that's flowing in between these two pools every year, and usually you see a non-constant rate. But we just simplify the question and see how matrix algebra play a role in solving this problem. Okay, so keep in mind that this is the problem that we're solving. And now we can describe this in a more mathematical way. So suppose that we have Fn is the size of the fast soil pool at nth year. So that's this Fn denotes the size of fast soil pool. So that's F. Slow, you have Sn. So that's the size of the slow soil pool at nth year. Because we know that every year that you have 95% of the fast soil pool will stay the same. So therefore, next year that you have Fn plus 1, which is the next year, is equal to the 95% times the current year, plus that you have 1% is coming from the slow soil pool. So therefore, we have this first equation here. And then at the same time, you will have the slow soil pool that you have 3% of fast soil pool will go to the slow soil pool. So therefore, 3% of Fn will contribute to the Sn plus 1, which is the next year, to the slow soil pool. And then 97% of the slow soil pool will stay the same. So therefore, we have these two equations. With these two equations, as you can see that if you know what is your initial values, we call it initial value, which is actually the fast soil pool and slow soil pool at the first year, you can compute 10 years after. Say, for example, if I know that the size of the fast soil pool here at n equals 1, okay, so say n equals 1, we have the fixed value for F1 and S1, then you have you can just substitute this F1, S1 to compute F2, and also substitute F1, S1 to compute S2, right? And then use F2 and S2, then you can compute F3 and S3, so on and so forth. You can get to the F10 and S10, and also any number, right? So this is an iterative computation. So let's convert this question further in the matrix algebra language. So say, for example, that I am using this vector notation. So this is something that we're going to cover. We're going to talk about this material. So if you're seeing this matrix notation, you're not feel familiar with, that's fine. We're going to talk about that. So let's denote this these two numbers. We call this vector. It's just a simple matrix that has one column, right? So we put the first soil pool size at nth year in here, slow here in the second row. So therefore, this is the vector xn, and that's the vector x. Sm plus 1 is going to be computed. You can use a matrix to multiply this current pool. So how does that work? Look at that. This is actually our xm plus 1. So that's the column vector, right? So because we denote this as the column vector, replace m by m plus 1, then this is your xm plus 1. And this is the matrix A, right? So that records the coefficients in the previous equation. Look at this equation, 95.1, 0.01, 0.03, 97. So just record those coefficients in this we call matrix, multiplied by another column vector. So this is something that kind of is coming from the matrix algebra. So therefore, when you need to compute the next year, you can use the matrix multiplied by the current year. And then we know that with this nth year, you can always compute n plus 1th year. So therefore, xn plus 1 is equal to a times xm. So that's the matrix times the current year. And the current year, this xn is equal to a times the previous year, and so on and so forth. So therefore, you can get to the point that where you keep substituting this matrix equation, you can get to the point that the n plus 1 years is equal to a to the power n times x1. So we're going to talk about this. This is something simple matrix algebra that we want to cover in this lecture today. And then also we want to talk about that this computation of a to the power n is sometimes computational expensive. So we want to come up with another idea to compute a to the power n. So because when the matrix A, this is a simplified model. We compute a square, a cube. This could be fast, but in general, computing the power of a matrix could be computational expensive when n is large. That means you have a lot of variables. Instead of just slow pool, fast pool, you have lots of pools in here. Then this computation can be simplified using the eigenvalue and eigenvector knowledge. So that's something that we're going to cover in this lecture as well. So stay with me if you feel this slide is kind of not very straightforward for you. Okay, so let's go through this first example, subsection about the basic operations. So we're going to talk about what are the dimensions, squares, what is square matrix, double subscript. So a matrix here this is a very standard matrix, and it's just a table that contains all the numbers. Could be real numbers, could be complex number, but most of the case that we're dealing in this research field, they are real numbers. And as you can see, it records the rate. We can record the rates from between pools. And this is the first thing that we talk about is the dimension. Dimension of this particular matrix A is 2 by 3. So we know that this is the dimension. The dimension of this matrix, we call it 2 by 3. And square matrix is a matrix when you have a number of rows equal to the number of columns. So in this case, this is not a square matrix, but if you look at the bottom one, this is a square matrix because the number of rows equals to the number of columns. And we also see this double subscript notation in the matrix algebra quite a lot. So this denotes this first subscript denotes the row index. And the second index denotes the column index. Say, for example, if you were referring to this number in first row, column 3, then that's A13. So A double subscript 1, 3. And if you are going to refer to this element 1 here in the row 2, column 2, then you have A double subscript 2, 2, right? So that's some standard notation that you always see in the matrix algebra. And matrix transpose is something you often see. It's just simply convert each row to a column. So we convert the first row to first column, second row to second column. That's the matrix transpose. And then some basic operations, add and subtract. subtract two matrices and just simply add and subtract the corresponding elements of the matrices. So that's very simple operations like the real in the real number system. And then scalar multiplication is also simple. If you have a number times a matrix, you just multiply this number to every element in this matrix. So that's why you have this simple example here. Slightly harder matrix operation is the matrix multiplication. So when you have two matrices X and Y, how do we multiply these two matrices? So first thing is that to multiply these two matrices, you need to check if this matrix multiplication is well defined. So when you have a X, which is the dimension with dimension m by k, and the matrix Y has the dimension k by n, then you could define the matrix multiplication. So to define the matrix multiplication, the number of columns in the first matrix has to be equal to the number of rows in the second matrix. So that's the basic requirement. So you must have that to define the matrix multiplication. And look at these two matrices. The first matrix is 2 by 3, and the second is 3 by 4, 3 rows, 4 columns. So therefore, number of columns is 3 in the first matrix, and the number of rows in the second matrix is 3. So therefore, you can multiply these two matrices, and then x, y. And once you can define this matrix multiplication, the dimension of the product, the product of these two matrices is going to be m by n. Just take out these outer dimensions, we call outer dimension, because when you put these two matrices together, the dimensions is really from these two outer numbers. So you take out this m and put here, take out this n here. So that's going to be the dimension of the resulting matrix. And therefore, let's talk about the details. So how do we do this in detail? So now we have X matrix and Y matrix. We're going to first compute this first row, first column, row 1, column 1 element. So to compute this result, so to compute this X, Y, the resulting matrix, you are going to have, first thing is that you notice that the resulting matrix in this particular example is a 2 by 3. So you will have a 2 by 3 matrix in this particular case. So we write out 2 rows, 4 columns, just leave them blanks right now, and then we're going to fill them out one by one. So we take out this first element. So how do we fill out this by -7? How do we know that's -7? We got it because this is the row 1, column 1 element. So we take out the row 1 from first matrix and column 1 from the second matrix, and multiply those numbers together element-wise, add them up. So that's -7. We fill this out. And then we move to row 1, column 2. Okay, so next we're going to compute the row 1, column 2. So row 1, column 2 is that we take out row 1 from the first matrix, column 2 from the second matrix, multiply those numbers together, add them up. That's -19. So therefore, this is -19. And next, we're going to look at this row 1, column 3 here. This is row 1, column 3. So we're going to take out row 1 in this first matrix, column 3 in this second matrix. Again, multiply, add them up, put it here, so on and so forth. And then after that, once you finish the first line, you move on to the second row. This is row 2, column 1. And similarly, you're going to take out row 2 in X and column 1 in Y. So that's row 2, column 1. And this is row 2, column 2. So you're going to take out row 2 and then column 2, so on and so forth. So I'm leaving it as an exercise for you to fill this out. And then I gave the final answer in the notes. So you can take a look at that. All right. So there are some important properties that that you need to know about the matrix multiplication. So first thing is that I gave them in the problems 5. I asked you to compute A, B, and BA. So and you will realize that A times B is not always equal to B times A. Therefore, we draw the conclusion that the matrix multiplication is not commutative, right? Because AB is not always equal to BA. And then, but then matrix multiplication is associative. So that means when you have three matrices multiplying together, it doesn't matter which two that you multiply first. You can multiply xy first, or you can multiply yz first, but you cannot shuffle the order, right? So you cannot do x times z. You cannot just times x and z together and multiply by y. So that's a very important difference between the matrix operation and the real number system. So this matrix system is when you shuffle the order of the when you multiply the matrices, you want to shuffle the order, it's very likely that you're making a mistake. Okay, unless it's a number. When you have a scalar like a constant number times a matrix, if it's a constant number, say for example k, you have x times k times y, then you can move this scalar multiplication around. But for matrix, you cannot do it in general, unless you know that unless you can prove that these two matrices, AB is equal to BA, then you can shuffle the order. So these two questions are a quiz one question that you can take a look, or you can pause the video and give a try on that. And the next thing we're going to talk about is the matrix equation. So matrix equation is that it's just like the idea of solving a equation for x. Say for example, you have a times x equals b, then you can solve x, and then x is equal to b over a, something like that. So for matrix equation, we're going to do this similar, but in this case, we will need to introduce the idea of inverse matrix and identity matrix. So first, for the identity matrix and inverse matrix, we always refer to square matrix. That means the number of rows and the number of columns are the same. So if when we talk about the identity matrix, they are square matrices, and then the dimension, if it's I2, then you have 2 by 2, I3 is 3 by 3, and IN is n by n matrix. And this identity matrix has the property that the main diagonals are 1 and the rest of the elements are 0. So this is these are called the identity matrix. And the role of identity matrix is like the number 1, just the number 1 in the real number system. So what does that mean? We really mean that when you have a matrix A times a matrix, another matrix, we call it A inverse. And if A times this A inverse is equal to A inverse times A equals the identity matrix, then we know that this is the inverse of the matrix. So it's just like the numbers when you have if in the real number system, say for example, 2 times half is equal to half times 2 is equal that, which is equal to 1. So this is something similar to the real number system, but instead of having a number 1, we are using this identity matrix as the real number 1 in the real number system. But the key difference is that here, when you look at this equation, when you have ax equals y, you solve this for x, right? If these three elements are all matrix, they're all matrices, then when you solve for x, here is the solution. This is the A inverse times y, and you cannot shuffle the order. As we know that shuffling the order in the matrix multiplication could result in something totally different. So how do we get that? Here is we left multiply if the matrix A has inverse matrix. Not every matrix has inverse, right? Some of the matrices has no have no inverse. So if the matrix has an inverse, so say for example the 0 matrix or a matrix that's a 0 row, so these matrices will not have inverse matrix. And more than that, there are more. These are just extreme examples. There are more matrices that each element in the matrix is non-zero. but however, they don't have inverse matrix. You can give some examples such as that when you have a matrix that 2 rows or 2 columns are identical. In those cases, those matrices will have no inverse. There are more examples than that, but in general, those topics will be covered in the 300 level linear algebra class. But in this case, we just make it simple. So say, for example, we know that the matrix A is invertible. That means it has inverse matrix. And to tell if a matrix is invertible or not, most of the computing programming platform will give you the function to detect if a matrix is invertible or not. You just type in the matrix and check if it's invertible or not. I will call it determinant, but if you've never heard about this terminology, that's fine. So this is the matrix A that we have here, that if it's invertible, then we left multiply this whole equation by A inverse, right? So you left multiply this equation by A inverse, then A inverse A is equal to the identity. So therefore, identity times a matrix is equal to the matrix itself. So it goes away. So the left-hand side equals X, and now the right-hand side, you have extra A inverse times Y here, right? So therefore, this X is equal to that. And then in problem 12, I was asking you to solve this equation for X. So you just left multiply this equation by A inverse, and then right multiply this equation by B inverse, then you get the X matrix, right? So you can solve this for X. And then a further example is this. You want to solve this whole equation again for X, right? Okay, so then you can move this BC to the left-hand side, and then you multiply this inverse 1 by 1. Okay, so you can take a look at the solution and then the whole process of how do we do that in example 1. And there is a quiz question coming after. So this is the matrix equation section. Right, and the next thing here is the linear system. Linear system is quite simple. That we've seen this in the high school. This is a linear system. It's a constant times a variable plus another constant times variable equals something. So this system has only 2 equations and in two variables. And in general, you will see a much larger linear system. So if you have 10 carbons pools, then you have 10 equations in 10 variables. So in this case, it just use this simple example as an illustration that we have to solve this linear system. We can do forward and backward substitution. But in general, if you remember what you learned in linear algebra, you can do Gaussian elimination and solve this and convert it to echelon form and then solve it, right? So with the matrix multiplication, you can also convert the system to this equation, right? So look at this equation. So it's going to be x1 times this column vector. This column vector are just coming from the coefficient of x1 in this here in these 2 equations, and plus x2 times that column vector. And the right-hand side is this is a vector that contains the right-hand side numbers. So this equation, this matrix equation, can be converted to, we call it this linear system can be converted to this, we call it vector form, right? So this is a vector form, right? So this is equivalent to the original system. If you multiply this, do this, we call the scalar multiplication, because x1 is really a scalar, because it's a number, right? It's a real number. We can just scalar multiply this x1, x2, add them up. And because left-hand side equals the right-hand side, so you have the first element in this left-hand side equals the first element on the right-hand side. That gives you the first equation. And second element in the left-hand side equals the second element on the right-hand side. So that gives you the second equation. So they're indeed the same, because we know that this case, x1 is equal to -2, x2 is equal to 12. So therefore, this left-hand side, after you substitute, this is equal to the right-hand side. So keep in mind that this is a solution of this example. We will use this example later. So That's -2 and 12. And then another way to solve it is to use inverse matrix, right? So inverse matrix is that we can convert this linear system in what we call the matrix form. So this is the matrix form that now you can multiply this row, first row, to the first column. So look at that. This is a matrix multiplication here. 2 by 2 times, this is first matrix is a 2 by 2 matrix. Second matrix is a 2 by 1. So in this case, the matrix multiplication is well defined. You can multiply out. You can multiply this first row by this column, then you get the first row here on the left hand side. Second row by this column, you will have a second row, first column in this left hand side. And because this is going to be a one column matrix and the left hand side equals the right hand side, set them up, you will row by row, you will have this linear system back. So therefore, this linear equation, this linear matrix, this matrix form is equivalent to the original form. And then solve this linear system for x, you can use the inverse matrix. So that's something that we just mentioned that in this in the previous section. All right, so that's linear system. Very simple. And in general, the linear system, solving a linear system could be very time consuming, and there are many algorithms solving the linear system numerically. But we're not covering here, but just keep in mind that the forward-backward substitution that you learn high school will work in no matter how big the matrix that you have, they will work. But in the actual algorithm that implementing in the system would not be that won't be that forward and backward substitution that you learn in high school. And the last piece in this lecture is the eigenvalues and eigenvectors. So we have this eigenvalues, eigenvector is being defined for, they are being defined for square matrix. So we only, when you have, we talk about eigenvalues and eigenvectors, they always refer to square matrices. So we say the x vector is an eigenvector if x does not equal to 0, and if there is a scalar such that a times x is equal to lambda times x. So this scalar is a real number, could be 0, could be 1, any real number. And then they sometimes could be complex. A scalar lambda is an eigenvalue if there is a non-zero vector such that a times x is equal to lambda times x. Okay, so here is something that is very important, and that is going to be applied in solving this problem 1 question. We know that a times x vector is equal a to the power n, which is that you multiply a, the matrix a, n times. So n of a multiplying together. This is equal to that. You can take out one of this a and multiply x, then you have n minus 1 left outside, right? So a times x. And this a times x, if we know that lambda is an eigenvalue of the matrix, then a times x by this second piece, if x is an eigenvector and lambda is an eigenvalue, then we have that this ax is equal to lambda times x. And then this lambda, we know that it's just a number, right? Just a real number or a complex number. You can just bring this in front, right? And then what's left is a to the n minus 1 times x. And again, we just split one of this matrix A out, and there will be n minus 2 left, the capital A multiplying together left outside, and you multiply a by x again. And if x is if lambda is an eigenvalue, x is the corresponding eigenvector, then you can do this substitution. Lambda, this is equal to lambda times x again. Then again and again, we do this again and again. Then you eventually will come up with this lambda to the n times x. And you see how convenient this is, because this simplify the matrix, the computation of a power of matrix. And Doing this, remember that when we have two matrices, when they are large, remember when we talk about the matrix multiplication, you take out rows, multiply the columns, and then you do this every row and every column, and then you finish this matrix multiplication. And when you have n of those matrices together, you will have to do this process n minus 1 time. So it takes a long time to get to the a to the power n. But however, if this can be converted to doing this power of a real number, then that will greatly simplify this computational process. And instead of doing this matrix multiplication, you can just raise the power n to a number, right? So that will make this computation much faster. So let's use this. So that's the purpose of this session. And then next, we're going to give a further example of what is how do we use this definition to verify if a vector is an eigenvector of a matrix. So we want to confirm these two vectors, V1 and V2, are the eigenvectors of this matrix. And keep in mind that this is actually the matrix that we got from the problem 1. Right, so in the problem 1 that we have this matrix, right? And how do we confirm that these two vectors are the eigenvector? You look at this definition. So you just need to verify that this matrix times the vector, this first vector, is equal to a scalar. So you just need to find out the scalar lambda times this vector -1 and 1. So V1 is -1 and 1. You multiply this matrix A by that, you get this -94, and second row is -0.94. Second row is 0.94. So therefore, there's a common factor. You can take out this scalar 0.94, and then what's left is just exactly V1. So therefore, you verify that this is an eigenvector because matrix times that is equal to the scalar times that. And you also, in addition, you also verify that 0.94 is a corresponding eigenvalue. Right, so very simple. Just use the definition, stick with the definition, you get the answer. And now you can verify the second one will be the same. Right, so remember that we are starting with these two equations in the problem 1, and we denote xn equals fn and sn. Therefore, xn minus 1 is equal to the matrix A. So just take out these these 4 elements and construct the matrix A. So next year is equal to this matrix A times the current year, and then this. Therefore, just starting from this equation, we're going to expand that. And xn equals xn plus 1 next year is equal to matrix A times the current year. And then this current year, xn is equal to A times the previous year, right? And we know that this matrix multiplication is associative. So you can multiply these two A's first, and then you get A squared. And then this xn minus 1 year is equal to A times xn minus 2, and so on and so forth. You can just doing this substitution, keep doing this substitution until you get to the x1, right? So you can stop at x1. Then therefore, the rest will be A to the power n, right? So you have A to the power n, you have those A's accumulates together, then you have A to the power n, right? And then if you remember, this can be computed using the eigenvalues. And so next, how do we use that eigenvalue and eigenvector? And x1, in example 4, we're going to set x1 to be 6 and 10. That means initially you have fast pool. The size of fast pool is equal to 6, and the size of the slow pool equals 10. Then by example 2, in that linear system, so that's why we talk about the linear system here. We know that solving the linear system, we know that this vector is equal to -2 times this vector plus 12 times this vector. I want to remind you that these two vectors are actually eigenvectors of the matrix A, right? So look at that. These two, we confirm that these two are the eigenvectors in example 3. So therefore, this x1 vector is equal to -2 plus 12 times v2. And this is x1, right? Because we use that to denote the carbon pool in the first year. So we call this x1. All right, so the first year, the carbon pool is equal to that. And remember that we want to find out n years after. So say, for example, we want to find out 50 years after. So therefore, n is equal to 50, right? So to compute x51, this is equivalent to to compute a to the 50, right? So just need to find out what is that. So therefore, what is that? A to the n times x1. We know that x1 is equal to that. Just substitute this x1 to this equation. Then you have to this function. Then we have that, and we can distribute a to the n to these two matrices. Then therefore take out this scalar. Then you have these two the sum of these two vectors. And what is that first? What is a to the n times v1? A to the n times v1, because v1 is an eigenvector. So with corresponding eigenvalue λ1, by the definition, we know that this is just λ1 to the power n. So look at that, we just mentioned in here, right? So we know that this is just λ1 to the n times v1. And then a to the power n times v2 is also equal to the corresponding eigenvalue to the power n times v2. So therefore, these two can be replaced. This number can be replaced by λ1 to the n times v1. This second one here can be replaced by λ2 to the n times v2. And what is λ1? λ1 is 0.94, and then we just substitute things here, right? λ2 is equal to 0.98 to the m. So I'm keeping these two notations, and v1 is the eigenvector -1 and 1. v2 is the eigenvector 1/3 and 1. And then this x1 is this 610. So therefore, this can be computed x51. So this is what we're looking for, 50 years after. This is equal to a to the 50 times x1. And x50, so a to the 50 times x1 is therefore equals that. So just substitute this n equals 50 into this equation. Then you get this, and I just did all this substitution, put it in the computer, let it compute it for you, and you will have this number. That means 50 years after, the size of the fast pool is equal to that, and the size of the slow pool is equal to this. Right, so that's the answer. And next, if I am asking you to compute this, I replace x1 by 26, and I ask you to compute the pool size 20 years after, what would be the answer? If the vector here is still the same, right? So I'm not talking about the quiz 3. If I'm still asking you this for this same vector, initial vector, initially you have this vector. What is the pool size after 100 years? And you know that for this question, you just replace n by n equals 50 here in this particular case by 100, right? So similarly, in this case, if you're still having the same initial condition, then 20 years after, you just replace this 50 by 20. But however, this x1 is different. So you need to find a way to come up with these two coefficients, because the matrix A is still the same. So the matrix A will have the same eigenvector. And you need to find out these coefficients using the forward and backward substitution you learn in high school, or you can just put it in computer and let it compute for you. And then you can and repeat this whole process and find out the answer for quiz 3. So that's it for this section. And in this section, just as a summary, we talk about, we solve the problem 1. We have the actual question, and to solve this problem using the matrix equation, we talk about the matrix operation, especially scalar multiplication, matrix multiplication. These are extremely important because we use that in this final in the problem 1. And then we talk about linear system, and linear system is also important because it gives us a way to decompose the vector into a linear combination of the eigenvectors. And then in the last, we talk about the eigenvalue and eigenvector. So this way will help us to simplify the computation of matrix A to the power n into the computation of a number raised to the power n. So these are the materials that we cover in this lecture. So thanks for taking this lecture with me. Right.